Hello dear students. So, in this video lecture we will be studying data mining and data warehousing, module 2, data warehouse implementation and data mining. So, in this video lecture we are going to see introduction to data warehouse implementation, efficient data cube computation, index OLAP data, indexing the OLAP data, OLAP server architecture, ROLAP versus MOLAP versus HOLAP, introduction to data mining, types of data, measures of similarity and dissimilarity. So, coming to the introduction of data warehouse implementation. As you know, data warehouse contains a huge volume of data. OLAP servers demand that decision support queries be answered in the order of seconds. So, as you know, data warehouse contains a large amount of data in terms of gigabytes and more than that. Whenever an OLAP server put a query, what we expect is the answer to the query will be within the seconds or less than second. Therefore, here it is crucial for the data warehouse system to support highly efficient cube computation techniques. We want a very fast cube computation techniques that whatever the query is being asked, immediately a particular cube has to be accessed, and from that data cube the answer is presented. So, we require an efficient cube techniques, computation techniques, access methods, how fast a data is accessed from a data warehouse, and a query processing techniques. So, in this section of data warehouse implementation, we present an overview of methods of efficient implementation of data warehouse system, explore how to compute data cube efficiently, how OLAP data can be indexed using either the bitmap indexing or the join indices, how OLAP queries were processed, and various types of the warehouse servers for OLAP processing. So, coming to the efficient data cube computation and overview. At the core of multidimensional data analysis, it is the efficient computation of aggregation across many sets of data. So, when you are dealing with multidimensional data analysis, what we expect? We expect is the efficient computation of the data across many sets of dimensions. If you take this into the SQL terms, these aggregations are referred to as group bys. Each group by can be represented by a cuboid, where a set of cuboid, where a set of group bys form a lattice of cuboids defining a data cube. So, we will take one group by, and these group bys, when they are combined, a set of group bys form a lattice of cuboid, and this lattice of cuboid is called as a data cube. One approach to the cube computation extends SQL so as to include a compute cube operator. The compute cube operator computes aggregate over all the subsets of dimensions specified in the operation. So, when we put a query of compute cube operator, so it will compute aggregate over all the subsets of dimensions in the operation. This can require excess storage space, especially for large number of dimensions. We start with an initiative look at what is involved in the efficient computation of data cube. A data cube is a lattice of cuboid. What is a data cube? A data cube is a lattice of cuboid, and what is a lattice of cuboid? A group of group byes or a set of group byes. Suppose that you want to create a data cube for all electronic cells that contains the following, that contains a city, item, year and sales in dollar. You won't be able to analyze the data with queries such as following. Now, what type of queries? Now, whenever I put this type of query, the data cube should immediately give me answer within seconds. Consider a query, compute the sum of sales grouping by city and item. So, here this query is asking you how many number of sales have occurred with respect to city and item. Next query, compute the sum of sales grouping by only city, means in which cities how much amount of sale has occurred, and compute the sum of sales grouping by item. What is the total number of cuboids or group byes that can be computed from this data cube? Taking 3 attributes, let us take 3 attributes, city, item and year. As the dimension for data cube and sales in dollars are measures, the total number of cuboids or group byes that can be computed for this data cube is 2 raised to 3, that is equal to 8. 2 raised to 3. So, here by mistake it is 23, this is 2 raised to 3 is equal to 8. The possible group byes are the following. How I can group the group byes? One group by may be city, item and year. Second may be city, item, city, year, item, year, or only city or only item or only year. And last one, a null. So, where this is the last one, it means that the group by is empty, that is the dimensions are not grouped in this case. The group byes form a lattice of cuboids for the data cube as shown in the figure. So, what all is present in this cuboid? The base cuboid contains all the 3 dimensions. So, that is this. The base cuboid contains all the 3 dimensions, that is 3D base cuboid, city, item and year. It can return the total sales for any combination of 3 dimensions. So, it will give you the total sales with respect to all the 3 dimensions. Now, first here this is the apex cuboid or a 0D cuboid, which refers to the case where the group by is empty, the apex cuboid is empty. It contains the total sum of all the sales. So, now this what it contains, the apex cuboid contains the total sale of all the sales, the total sum of all the sales. The apex cuboid is the most generalized or least specific of the cuboid and is often denoted as all. So, this can be represented here, apex cuboid 0d can be represented as all, because it gives you sum of all the sales with respect to the city, item and year. If you start at the apex cuboid, if you start from the apex cuboid and explore downward in the lattice, this is equivalent to drilling down within the data cube. So, if you start from here and start moving or start drilling down within the data cube, this is equivalent to drilling down within the data cube. If you start at the base cuboid and explode upward, that is akin, or if you start from here and start moving upward direction, that is called as a rolling up operation. Okay. So, here 0d cuboid will give you all the sales with respect to all the 3 items, whereas this 1d cuboid will give you sales with respect to city, this cuboid will give you sales with respect to item, this cuboid will give you sales with respect to year, and this cuboid 2d cuboid will give you sales with respect to city and item, this will give you with respect to city and year, this will give you with respect to item and year, and this is giving all the 3 dimensions city, item and year. Now, let us take an SQL query containing no group buys. Example, compute the sum of total sales is a 0 dimensional operation. Okay, so, it is compute the sum of total sales, that is at 0d apex cuboid, is a 0 dimensional operation. An SQL query containing one group by, example, compute the sum of sales group by city. So, that will, so here this one. So, this is an query compute the sum of sales group by cities, it is a 1 dimensional operation. A cube operator on n dimensional is equal to the collection of group bys by statement 1 for each subset of n dimensional. Therefore, the cube operator is the n dimensional generalization of a group by operator. Similar to the SQL syntax, the data cube in the example can be defined as define cube sales underscore cube is equal to city in bracket city item here is equal to sum sales in dollars. For a cube with n dimensions, there are total 2 raised to n cuboids. Okay, again here this is 2 raised to n cuboids including the base cuboid. A statement such as compute cube sales cube would explicitly instruct the system to compute the sales aggregate cuboid for all the 8 subsets of the set city, item and year including the empty subset. Online analytical processing may need to access different cuboids for different queries. Now, data warehouse will be dealing with online analytical processing system or OLAP systems, and this OLAP system may need to access different cuboids for different queries. Therefore, it may seem like a good idea to compute in advance all or at least some of the cuboids in a data cube. So, before only in a data cube we will compute all the data, and whenever a request comes immediately the answer is presented. So, it is not like once a query comes we start computing the cuboid and start giving the result. So, therefore, it is a good idea to compute in advance all or at least some of the cuboids in data cube before only. So, what is the advantage of that? Pre-computation lead to the fast response and avoid some redundant computations. A major challenge related to this pre-computation, however, is that required storage space may explode if the all the cubites in a data cube are pre-computed. So, now the problem with this method, so if I pre-compute the data before a query comes, before only I will pre-compute a data, what is the problem? The problem is that, so here we will face a major challenge. What is that? Pre-computation will lead into a requirement of large storage space. Usually when you have a huge number of dimensions, the storage requirements are even more excessive when the dimensions have associated concept of hierarchies with multiple levels. The storage requirements will be even more excessive when many of the dimensions have associated concept hierarchies with multiple levels. This problem is referred to as the curse of dimensionality. Okay. Now, let us come to the point, how many cubites are there in an n dimensional data cube? If there were no hierarchies associated with each dimension, then the total number of cubites for an n dimensional data cube will be 2 raised to n. That is a simple thing. If there are no hierarchies associated with a data cube, then it will be directly 2 raised to n. However, in practice many dimensions do have hierarchies. For example, time is usually expressed not only in one conceptual level, example year, but rather a multiple conceptual level as a day, month, quarter and year. We usually do not access the data by a year. How we access the data with respect to day, day to the month, month to the quarter and to an year. For n dimensional data cube, the total number of cubites can be generated, including the cubites generated by climbing up the hierarchies along each dimension, is total sum of cubites t is equal to, for all I equal to 1 to n, L of I plus 1, where L of I is the number of levels associated with the dimension I. 1 is added to L of I is to include the virtual top level. So, that plus 1. So, why this 1 plus is added? So, 1 is added to L of I to include the virtual top level all. Note that generalizing to all, it is equivalent to the removal of dimensions. This formula is based on the fact that at most one abstraction level in each dimension will appear in a cubite. For example, the time dimension as specified before has 4 conception levels, or 5 if we include the virtual level also. If the cube has 10 dimensions and each dimension has 5 levels, the total number of cubites that can be generated is 5 raised to 10, that is equal to 9.80 to 10 raised to 6. The size of each cubite also depends on the cardinality, that is the number of distinct levels of distinct values of each dimensions. For example, if all electronic branch in each city sold every item, there would be city into item tuples in the city item group by alone. As the number of dimensions or the number of conception level hierarchies or cardinality increases, the storage space required for many of the group bys will grossly exceed the fixed size of the input relation. By now, you probably realize that it is unrealistic to pre-compute and materialize all of the cubite that can be possibly generated for a data cube. If there are many cubites and these cubites are large in size, a more acceptable reasonable option is partial materialization, that is no materialize, that is to materialize only some of the possible cubites that can be generated. If there are many cubites and these cubites are large in size, what is a more reasonable option is partial materialization. So, here we are not going to materialize each and every qubite, we are going to materialize or pre-compute only a part of the cubites, that is to materialize only some of the possible cubites that can be generated. So, if I materialize every qubite, that is called as full materialization. If I do not pre-compute any of the qubite, then it is called as no materialization, or if I pre-compute only some of the qubite, that is called as partial materialization. Now, how we have to materialize, whether we need to go for full materialization or we need to go for partial materialization or we should go for non materialization, that depends on selection of which qubite to materialize will be based on size, sharing, excess frequency, etc. Now, coming to the next point, what is partial materialization, selected computation of cubites. There are three choices for a data cube materialization given a base qubite. So, first one is, there are three choices, one is no materialization, full materialization and partial materialization. So, no materialization is do not pre-compute any of the base qubite. So, we are not computing any of the non-base cubites over here. Do not compute any of the non-base cubites. This leads to computing expensive multidimensional aggregates on the fly, which can be extremely slow. Whenever a query comes, then we need to go for computation of every qubite, and that will take a much time for a query to be processed, and this will lead into extremely slow system. Then coming to the full materialization. So, in full materialization, pre-compute all the cubites. The resulting lattice of cubites is referred to as a full cube, but this choice typically requires a huge amount of memory space in order to store all the pre-computed cubites. If I pre-compute the cubites, then it would require a huge amount of memory space. Next, coming to the partial materialization. So, selectively compute a proper subset of the whole set of the possible cubites. So, now here you need to select some of the cubites, not all. So, partial means only we are going to pre-compute some part of the cubites. So, we may compute a subset of the qubite which contains only those cells that specify some user defined criteria. So, now in a partial materialization we need to take in consideration some user defined criteria, such as where the tuple count of each cell is above some threshold value. For that qubite only we are going to pre-compute. So, here we will use the term called as subcube to refer to the later case, where only some of the cells may be pre-computed for various cubites. Partial materialization represents an interesting trade-off between storage space and response time. So, here always there is a trade-off between the storage space and response time. Whether you want to, if you pre-compute qubite, then a huge amount of storage space is required and the response time will be less. But if you pre-compute less number of qubits, storage space required will be less, but the response time will be more. So, partial materialization of cubites or subcube should contain or should consider three factors. First one, identify the subset of the cubites or subcubes to materialize. Now, first thing is you need to identify which subset of cuboids or subcubes you are going to materialize. You need to identify them. Exploit the materialized cuboids or subcubes during query processing. So, whenever a query comes to get some value from the cuboid, the first thing what you need to do is exploit the materialized cuboids or subcubes. Then efficiently update the materialized cuboids or subcubes during load and refresh operation. So, whenever a new data is loaded, whenever a data is refreshed, you need to efficiently update the materialized cuboids or subcubes, so that you will get the updated data. Okay. So, in this video lecture, we studied what is the introduction to data warehouse. So, how a efficient data cube computation can be done, what is a data cube, what is a group by, what is the layers of cuboid. We saw some of the queries and we saw how we can efficiently execute them. So, then we studied a lattice of cuboids making up a 3D data cube. This structure contains apex cuboid to base cuboid with and 1D and 2D cuboids. So, where each cuboid represented different group by, and the base cuboid contains the city, item and year dimensions. Then we also studied how to execute a SQL query. We took one example. Then we also calculated how many total number of cuboids that are required. Then we also discussed what is materialization, that is no materialization, full materialization and partial materialization, and what are the factors that need to be considered whenever we are going for partial materialization. So, we come to the end of this video lecture, and in the next video lecture we will be discussing indexing of the OLAP data using bitmap index or the Jian index. So, we will come to the end of this video. Thank you, one and all.